So what happens if your treatment is actually not random? So before we had an RCT, and now we don't have an RCT, we have a conditional independence assumption in this case. So what we see is that we can see that by regressing job help, which is treatment, on all of our variables in our dataset except for the wage, our outcome variable. So let's do tidy. And as you can see, the treatment is quite related with gender, with ethnicity, with the number of priors. So it's not like our treatment is really random. So what happens? So if we run a linear model of wage on all the variables, treatment and all the other variables as controls, we get that the treatment effect is $93. Whereas we know the truth. The treatment effect is $71, the average treatment effect. Whereas here, we overestimate the average treatment effect because of the non-random selection, even after we control for all other characteristics. So let's see what happens if we run a causal forest. We are asked to fill in the blanks below to basically do the causal forest again, the second one. So x2 is the new variables. So dataset 2. So what we do, we remember deselect wages and wage and deselect job help, that's the treatment. And then what do we do? Model matrix. Where we do like this, and data is equal to the placeholder plus pipe it again, so it's the same code. Now then we deselect the intercept, and then we run the new causal forest where our new values are x is equal to x2, our outcome variable is wage from the dataset 2, and our new treatment is from the dataset 2, job help. Number of trees, I don't remember, let's do 4,000, right? That was the before. Clusters null, sample fraction 0.5, honesty true, tune parameters all. Then show us what happens there and show us what is the average treatment effect of this newly trained forest with this where treatment is not completely exogenous, and treatment sample all. Okay, let's run it. It will take some time because it's also tuning all the parameters. And finally we get, it estimates the treatment effect to be $83. So OLS estimated at 90 what? $93. Causal Forest estimates at $83. We know that the true effect is $71. So the Generalized Random Forest actually calculates average treatment effect, which is not completely wrong. Not same as the OLS result, it's better because it's closer to the truth. Not same as the true average treatment effect. Not below, but slightly above the true average treatment effect, but still better than the OLS estimate. So why is Generalized Random Forest performing better than the OLS? So Generalized Random Forest actually employs the same thing as double machine learning. So basically the formula for the causal forest actually has hidden y hat and w hat. So in fact we can supply our own predictions for y and predictions for w, and then it will just regress the residuals on residuals. So what it does this under the hood. anyways. Even if we have completely random assignment to treatment, it does this anyways. So now we can do this by hand ourselves, the same steps as Causal Forest does it under the hood. And it means that you can use this formula, Causal Forest. You can run, I don't know, something else outside in like not a regression forest. You can run a lasso or an OLS or whatever. You can do different predictions using different methodologies, and then you just supply this part, and you can still use Causal Forest. So again, let's go. Forest W. We do a regression forest where x is x2, y is data set 2, and here be careful, it's w, right? So we want to partial out our control variables from the treatment, so it's job help. Tune parameters all. You can pass many more other parameters, we just do the minimum here. Then you predict forest W. You get predictions, out of bag predictions for the treatment. You do the same for the outcome variable, which is data set 2 and what was wage. Yep. Tune parameters all. So see, we do double machine learning here, where we don't do cross-fitting simply because the prediction is our out-of-bag prediction. So it's anyways is done on a separate sample than the model was trained on. So everything is good. So here we predict, but based on forest Y. So we collect our predictions of the treatment and our predictions of the outcome, and then we run the causal forest where x is x2. Let me just copy the code from here. Y is wage, W is job help, Y hat is Y hat that we just trained, the predictions that we just got, W hat. So, and tune parameters all. And then we want to see the average treatment effect of C forestry. Target sample all. Okay, $83. The same as, almost the same as in here. So you see, this Causal Forest 2 was also running 2 regression forests to predict Y and to predict W, but we just, by not specifying Y hat and W hat, it does it by itself. Now, here is the code where I basically show you that if there is very important unobservable which is not captured in our data, then the generalized random forest will fail. And I mean, any methodology will fail because we still need to observe the confounders to be able to somehow say something about treatment effects. But as you can see, even here, it's not that great. So it's still $10 difference between what we estimate using the generalized random forest and the true treatment effect. So we take a new data set which has important confounder that is not in the data. And so if we run the code, actually it's already run for us because there's nothing we need to do here. It just shows that point estimate of the treatment effect is $120. So because there was some important confounder which is not in our data and none of the other variables can approximate those confounder, and we are missing it, we vastly overestimate the average treatment effect. If before we said it was $80 versus the true $70, now it's $116. That's it.